blood cancer is like a bodily imposter. No, not like that. Well, actually, maybe. Think about this. Hello and welcome. Today, we're going to explore the mathematical underpinnings of a vital biological process, the growth of cancer cells, specifically blood cancer cells, through the lens of exponential functions. In the bustling city that is our body, the bloodstream is a highway of life, with red blood cells and white blood cells all playing their crucial roles. Our story begins in the bone marrow, the blood cell factory. Here, cells are born, mature, and sent off to work, maintaining the delicate balance of our health. But let's zoom in on a twist of fate, a mutation. Just one incorrect letter in the vast DNA sequence can set off an unexpected chain reaction. This is where blood cancer, such as leukemia, starts. It's like a factory error that doesn't stop hitting the button, producing more and more defective cells. Now, imagine plotting the numbers of these cells over time. What you'd see isn't a straight line, but rather a curve that races upwards faster and faster. This is what you call exponential growth, and it's how blood cancer cells multiply. Now, the math behind it is pretty straightforward. It uses the equation y equals a times 1 plus r to the power of t. A is the initial number of cells at hour 0. Because the number of cancerous cells is to increase, we use the number 1 in addition to r, the rate expressed in decimal form. In this video, we'll use the whole number 1 expressed as 100% in percentage form. We'll use this as cancer cells typically multiply through doubling themselves. T is time, expressed in hours like we'll do today, and last but not least, y is what we're solving for. It's essentially the number of cells after a number of initial cells, the r rate, and t time. Now, by manipulating the function, changing the value of t basically, the time in hours, we can model cancer progression through just this single variable. That's pretty cool. Now on the screen is something that completely shows how a cancer cell duplicates itself. Now the cancer cells double in each round, which is basically the reason why we use the whole number 1, which is, as I said, 100% in percentage form. Now let's begin our first problem. A patient is diagnosed with stage 0 blood cancer. That means that there's not enough cancer cells to create a cancerous tumor. His doctor knows that at least millions of cells must be present for a tumor to form. However, she wants to know how her patient's cancerous cells will increase over time to model the correct time for treatment. Currently, the patient has around 100 cancer cells present in his body. At hour 1, how many cancer cells will have been formed in the patient's blood? How about in hour 2? And how about in hour 5? Okay, that was a lot to ask for. Let's start with hour 1. Using the equation we just learned, let's fill in the variables. As written on the board, A is 100, which means that there's 100 initial cells. R is 1, the rate expressed as a decimal, and lastly, we fill in T as 1. Now that we've gotten that at hour 1, we'll have 300 cancerous cells, let's go on to answer the second problem that they asked for. What happens in hour 2? Let's fill in the same values for A and R, but let's change the value for T, as it's going to be hour 2. Now we have in the equation y equals 100 times 1 plus 2 to the power of 2. Now we exponentially get a higher number, which is 900 cells. Now let's plot that on the graph that we have on the right. Finally, let's go on to the last part of this problem. How many cancer cells will be there at hour 5? We'll have the same steps, but we'll have t equal to 5. The final answer that we get is 3,200 cancerous cells. Now, the graph on the right does not give justice to how big this number is, so we're going to be graphing this on Desmo. pretty easy, right? Like we just saw, cancer cells grow exponentially, thus proving to be harmful and perhaps even deadly. Thankfully, that's where treatments like chemotherapy and immunotherapy come in. But that's for a different story. So undoubtedly, mathematics offers a glimmer of hope. The mathematics of these functions are not just abstract concepts, but are applied to life-challenging medical practices. And by understanding the exponential function, researchers can develop treatments that target the rate of cancer cell growth, aiming to restore the delicate balance of our bloodstream. Thank you.